Hello everyone, welcome back to Discrete Mathematics with me Adila Krishnadi. So in our previous videos we've seen or we've discussed the notion of bipartite graphs, and we've seen a way or a technique to determine whether a graph is bipartite. Now we look at after that we look at the problem of matching, which was used as a motivation to bipartite graph. Let us define matching for every graph, for every undirected graph in general, and then we will look at the case of bipartite graphs, matching in bipartite graphs. So matching is actually just a subset of edges. So a matching is a subset of edges, but with condition that no two edges in the matching are incident at the same node. So that's matching. So for example, a very simple example, if you have a graph look like this, then the matching would consist of, this is a matching, this is a matching, and the combination of them is a matching. So if we rename this A, B, C and D, then A, B is a matching. Sorry, the set containing this is a matching, and then this set is also a matching. So is this set. Yeah, so this is a matching, this is a matching, and this is also a matching. So a collection of a collection of edges. Well, of course there are others, right? For example, this is a matching. Yeah, so matching is simply just a subset of the edges of the graph, and with the requirement that no two edges incident at the same node, right? Now if a node occurs as an endpoint of an edge in the matching, then we will say the node is matched. So for example, in this case, A is matched, so is B. So A is matched to B actually. But in this matching, C is not matched, D is not matched or unmatched. Yeah. Whereas here you see that every node are matched. Now, of course, if in a matching, the edge cannot be a loop, right? Because yeah, well, because their endpoints are all different. So to be more precise, a matching is really just between different nodes. Now, matching, of course, can exist as we see here. Well, matching can exist in non-bipartite graphs, but in a bipartite graph, finding matching is usually easier. And also, a graph can contain more than one matching. So because a graph can contain more than one matching, then the question is, we could consider, or we could define a number of particular matching. So for example, we could say that a matching M is maximal if and only if M is not a proper subset of any other matching, meaning that we cannot add more edges to M. Yeah, to M. Yeah, we cannot add more edges to M if M is maximal, meaning that if we add another edge to M, then M no longer becomes a matching, so we will lose the matching property. Now there is also a notion of a maximum matching. Now maximum here is defined with respect to the size of the matching, so meaning the number of edges in the matching. So a matching is maximum if the number of edges in the matching is larger or equal to every other matching in the graph. Yeah, so the number of edges is maximum. And also a matching is perfect in a graph, so any graph, if all nodes are matched. Yeah, all nodes are matched. Yeah, so, and finally, special for bipartite graph, because in bipartite graph you could have you will have two sets, v1 and v2, two sets of nodes, disjoint sets of nodes. Then we could define a matching to be complete from v1 to v2 if every node in v1 is matched with some node in v2. That is, the size of the matching is the same as the size of v1. Note, of course, perfect matching must be also maximum matching, yeah, because all nodes are matched, and also maximum matching is definitely a maximal matching, but maximal matching may not necessarily be a maximum matching. Also note that perfect matching, in a perfect matching, then if a graph has a perfect matching, then the number of nodes must be even, and the size of that matching, that perfect matching, is half of the size of the node. So let's see some examples. So here we have essentially the same graphs, so one graph, but we see four different matchings. So in the upper left, we see so this graph has eight nodes. So any perfect matching must be of size 4. So you see here is an example of a perfect matching. So the matching matches A and B, C and E, G and H, F and D, and you see that these edges A, B, C, E, G, H, and D, F, they don't share any endpoints. Yeah, they don't share any endpoints. Now here the size, this is a perfect matching because every nodes are part of the matching. Similarly here, right, so you see here this is another perfect matching, so you could have actually two different perfect matchings. Yeah, look at the red edges. Yeah, so this is another perfect matching, also with the size 4. There is no matching of size 5 because there are only 8 nodes. Now on the upper right here, we have a maximal matching. In this case, so look at this, the matching consists of 3 edges, so F, G, H, E, and B, D. Now you see this is a maximal matching because whenever we add any other edge, then for example, let's say if we add A, B, then it will no longer be a matching because B occurs in 2 edges, or 2 edges are incident at B. So we cannot add AB, we cannot add AD, we cannot add BC, and so on. So this is maximal. So because we can no longer add another edge to the matching. Do we have another maximal matching? Right, yes we do. For example, this one, it is a matching, so with 2 edges, and in this matching this is also maximal because you cannot add any more edges to the matching. If we add another edge, then the matching will lose the matching property. Right, so that's an example of a graph. We have 2 perfect matching in a graph. We have 2 maximal matching of different size in the graph, right? Now let's have a look at another example of here. Here's another graph, different one than before. In this graph we have 10 nodes. So any perfect matching matching must be of size 5, right? Now let's have a look at this graph. So Here is an example of maximum matching. So yeah, here, so this matching is of size 4 and it is maximal, yeah, because you cannot add any more edges to it, so that without losing the matching property, matching condition. Similarly also this one, yeah, you cannot add any other edge, so it is maximal. And is this maximum? So the question is there a matching of size 5? Well, the answer is unfortunately no, right? So for example, let's say we know that j is of degree 1 here. So if we wanna, let me erase this just to illustrate, right? Yeah, so if we wanna add j to a matching, so j must be paired with h, right? Now because j must be paired with h, then we are left with G, D, I, F, C, B, A, and E, right? Now, next, because of that, G can no longer be paired with H, so is E. So G must be paired with D, and also I must be paired with F. Now, if this is the case, then we cannot add a pair involving E, right? Yeah, because if we add a pair involving E, yeah, then we will involve D, and or we will involve F, which violates the matching property. So if we have a matching involving involving J, then E cannot be part of the matching, and vice versa. Actually, if you start from E, then J cannot be part of matching. Yeah, so that's the reason why there is no matching. So the answer is no here. There is no matching of size 5 here, so therefore a matching of size 4 will be maximum. Now let's see how this matching problem is applied to bipartite graphs. So let's recall the employee table that we've seen in the first slide. So here the idea is we want to match the employee to the task, so that of course the employee must is assigned task that is part of his or her expertise, and also an employee is assigned exactly each task is assigned to exactly one employee, and no employee is given more than one task. So just look at this table and let's see how this is modeled as a graph. So we model the expertise as follows. So suppose you have Andy, you have Benny, you have Chitra, and you have Desi, and you have the tasks and the expertise, requirement analysis, architecture design, implementation, and testing. Now if we look at this and then we map, the expertise of Andy is requirement analysis and testing, and then expertise of Benny is architecture design, implementation, and testing, and then Chitra has expertise in requirement analysis, architecture design, and then implementation, and then Desi has expertise in architecture design, right? So well, apologies if the picture looks a bit messy, but well, at least you see the relationship. So now we want to see whether there is a matching. Now obviously, so we want to see whether there is actually a complete matching from the set of employees to the set of tasks or expertise. Now a complete matching means that from employees to the expertise means that every employee will be assigned a task, right? So now let's see. So Desi, here must be assigned RA, right? Because, well, Daisy can only do RA, requirement analysis. Now, because Daisy is assigned RA, then essentially we take out RA from the equation, right? From the matching. So that means Andi can no longer be matched to RA. Chitra can no longer be matched to RA. So let's see. That means, let's see. Andi can only do requirement analysis and testing. Now, because requirement analysis has been taken by Daisy, so therefore Andy must do testing, right? So now testing is taken out, yeah, and because of that, Benny cannot do testing, and, well, Chitra cannot do requirement analysis. Now the rest is simply just, now because Chitra and Benny can do both architecture design and implementation, then we could choose Benny to do architecture design and Chitra to do implementation. So this is one matching, yeah, and this is complete, yeah. And then, of course, another complete matching from the employee to the task is Daisy RA, Andy with testing, and then Benny to do implementation, and then Chitra to do architecture design. So we have two complete matching in this case. So that's hopefully clarifies the concept of matching. Now, another example here is the general situation. Suppose we have a M men and N women in an island, and suppose that everyone has a list of names of their opposite gender who he or she can accept as husband or wife. Now, the matching here, so the matching can be solved using a bipartite graph. So essentially, a graph G, V1, V2. Let me write it on slightly better. So G, V1 union V2 E, where V1 is set of men and V2 is set of women, and of course the size of V1 is M and the size of V2 is N. Now, and an edge, so M is connected with a man is connected with a woman, if and only if, well, M is willing to be paired as a husband of W, and that woman is also willing to be paired as a husband, as a wife of M. That is, M is in the list of that W has, and M, so NW is in the list that M has. Right. Now, a matching is then simply a graph whose edges, or a subset of edges, yeah, you could see this as a graph as well, whose edges are between men and women who are actually paired as a husband and wife. So that means the choices, right? So the actual choices, yeah. And then a maximum matching, then the largest possible set of husband-wife pairs that can be obtained, yeah, that will be a maximum matching. And a complete matching from V1 to V2 is the set of husband-wife pairs such that every man is married to some woman, but maybe not, but maybe not every woman is married to a man, right? Because, for example, the woman, maybe you could have more women than men. So that's the intuition behind behind maximum matching and complete matching in bipartite graphs. Alright, so now let's do some exercise. So this is the employee situation again. This time we still have 4 employees. with their expertise. Here Sony has expertise in architecture design, and then Tony has expertise in requirement analysis, implementation, and testing, and then Winnie has expertise in architecture design, and then Yeni is in requirement analysis, architecture design, and testing. So can we assign a task to each of the employee to finish the project? So the task is requirement analysis, architecture design, implementation, and testing, so that each task is assigned to exactly one employee and no employee is given more than one task. Right, let's try this exercise first, and then we shall discuss the solution in the next video.